Hello everybody, this video is going to cover equilibrium constants and equilibrium quotients. So when we have a reaction and it reaches equilibrium, you are not always going to have equal amounts of product and reactant. Remember that the equilibrium point is the point at which the rates of the forward and backwards reaction are the same. That doesn't mean the quantity of reactants and products are the same. So if a reaction has more products when it's finished, we say it's product favored. If a reaction has more reactants left when it's finished, we say that it's reactant favored. So once you reach that equilibrium point, you can look to see, how much of everything do you have? Is it product or reactant favored? You often see it represented in these little graphs. Once you reach equilibrium, maybe you haven't used up a lot of reactants, so you still have a lot of them left. Or maybe you've made a ton of products and you only have a little bit of reactants left. We're very interested in the quantities that we have, so we'll be doing a lot of calculations trying to find the concentrations that exist once you're at this point. Remember that your reactants and products are all contained in the same beaker. They're all present at the same time. They're all in the same container. So we can figure out the concentrations of each. So when we want to know whether or not something is product or reactant favored, we look at a special number that we can calculate. We're going to look at what's called the K value, the equilibrium constant. KEQ is the equilibrium constant. It's going to allow us to decide and determine if you have more products or reactants. It's going to be a ratio. So here's the generic. You're going to take the concentrations of your products and you're going to divide it by the concentration of your reactants. If you have a lot of products when you're finished, your K value is going to be greater than 1. If you have a lot of reactants left when you're done, right, you're dividing by a big number, you're going to end up with a K value that is less than 1. If for some crazy coincidence you happen to have equal amounts of everything, then your K value would equal 1. It's just very unlikely to happen. Sometimes our K values are very, very, very large with huge exponents, meaning that almost everything turns into products. Sometimes they're very, very small, meaning very little product gets made. It's not a reaction that likes to happen. You may have exponents that are very, very small, like negative numbers, to get a very small K value. Calculating this is a little bit more complicated than it looks in the generic example. So let's kind of go over how we would do this for real. If we want to calculate the equilibrium constant, we use this thing called the law of mass action. That's basically describing how you set up your equilibrium constant calculation. It's going to be products over reactants. If we have this as our generic example, the lowercase letters are our coefficients. And this is how you set up a law of mass action. This is how you calculate your equilibrium constant, your K value. You put the concentrations and then you raise it to the power of whatever exponent you had. Of whatever coefficient you had. That's going to become your exponent. If you have 2 reactants, you have 2 things on the bottom. If you had 3, you'd have another one over here. If you only had 1, you'd have 1 thing down here. You do this for however many chemicals you have. One really, really important thing to understand is that these square brackets represent concentrations. And you have to remember, that solids and liquids do not have concentrations. A solid and a liquid are not showing up in this calculation, okay? One thing to understand that not all teachers kind of go over is the fact that how we write our law of mass action is actually simplified. There is an additional part to this calculation that is really far and above beyond what we're going to do here. And it's a correction value, and it will help get it so that your K value has no units left over. We will never worry about that. If you get on the internet and you start looking up stuff, you may see these extra things thrown in. Most high schools don't cover that, so don't worry about it. Let's do a practice problem. I'd like you to try to write the equilibrium expression, the law of mass action, however you want to say it, for this reaction. Remember, you're going to put your reactants on the bottom, inside square brackets. The exponents are going to be the coefficients that you see. Your products go on the top, inside square brackets, and the exponents are the coefficients. So pause the video and try to write out that equilibrium expression, that law of mass action. All right, so on the top, I'm going to have these two. The nitrogen monoxide will be squared because we had 2 as a coefficient. The exponent for my oxygen is just going to be a 1. My nitrogen dioxide is going to be on the bottom, and it will also be squared because it had a 2 coefficient. You do not have to write the 1 up here. Just like in math class, we don't usually write 1x. You don't have to write it here. I wouldn't take points off if you put it. It would just be a little bit extra. Now, when we're writing this, you might have noticed that we used a double-sided arrow, which implies the reaction can go both ways. But we wrote the equilibrium expression assuming we were going in the forward direction. It's really important that you understand that we always assume that we're going forward unless you're specifically told to go backwards, okay? So if I ask you to do the backwards reaction, what you're going to do is you're just going to flip it, because now what your reactants were are now products, and what your products were are now reactants. So that's just flipped. So you try to write what the backwards K value would be. Instead of saying K equals, you're going to use a little apostrophe at the top. We call that prime, so K prime. That's telling people that you've made a change to it. We're going backwards. All right, so this is what we end up with. Since we're going this direction, now this thing over here, right, on this side is now our product, and these were now our reactants. So that's why you see them in the places you do. You should notice that the exponents don't change because my coefficients did not change. And if we just want a generic version, there we go. I'm never going to, well, I guess I can't say never, but I would be surprised, I wouldn't expect me to ask you to rewrite the entire equation backwards. Just flip your law of mass action, just flip your K expression. Next question that tends to come up is, well, what if instead of having aqueous things with concentrations, what if we have pressures? Because we can do this for gases as well. So if you have gases, you're going to have pressures. So you just use their partial pressure the same way you would use a concentration, because that's the equivalent, isn't it? One important difference, now if you end up taking AP Chem, they're super strict about this. You only use square brackets for concentrations. Therefore, for our pressure, you need to use actual parentheses. I know that seems trivial, but people really, really care about that, okay? So that is something that we will be picky about as well. So sometimes people will ask, well, how can you tell if a reaction is at equilibrium or not? What if it hasn't gotten there yet? Well, what we can do is we can use these law of mass actions, these equilibrium expressions. We can plug in the concentrations or the pressures that we do have, and we can see if it equals what the K value is supposed to be. So you're going to calculate with the numbers that you're given, and you compare it to the known K value. We call that a reaction quotient. If you don't know whether or not you're at equilibrium, if you are plugging in numbers to your expression to check if it's at equilibrium, we call that the quotient. We use a capital Q instead of a K. So you would plug in your numbers, you would calculate Q, and then you have to stop and think, okay, what is the Q value going to tell me? Well, if your K equals Q, then you are at equilibrium. If you plug in your concentrations and it matches your K value, great, your reaction is at equilibrium. Now, if your K value is smaller than Q, if Q is too big, that means the numerator of Q was larger than it should have been. The denominator was smaller than it should have been. That's telling you that you have too many products in your beaker. So what's going to happen is the reaction is going to shift to the left, trying to break apart some of those products, right, and put them back into the reactants. The backwards reaction is going to proceed until you get to your equilibrium point. Now, if you dump your chemicals in the beaker, you calculate your Q value, and Q is too small. Q is smaller than K. What that's telling you is that you don't have enough products, right? Your numerator is too small, your denominator is too big. You have too many reactants and not enough product. So the reaction is going to proceed in the forward direction. You're going to shift to the right until you've made enough product to be at equilibrium. So the Q value is going to help you predict which way is going to proceed. Is it going to go to the left? Is it going to go to the right? Is it going to be the backwards reaction or the forwards reaction dominating? There's another reason why the equilibrium expression and equilibrium constant is so important. And that's because it will allow us to calculate the concentrations that we might need. Sometimes when you're doing chemistry experiments, you're trying to force certain things to happen. You're trying to force a reaction to proceed in one direction instead of the other. So if you know what your K value is, you can make decisions about what concentrations to put in your beaker to force the reaction to do what you want, basically. Let's do a problem where you have to decide if you're at equilibrium or not. And if not, which direction would the reaction proceed? Forwards or backwards? To the right, to the left? So here's the practice problem. Given this generic equation, at a particular temperature, your K value is 1.4 times 10 to the 3. If you mixed 1.2 moles of Y, 0.07 moles of Z, and 0.003 moles of X in a 1 liter container, in which direction would the reaction initially proceed? So what you need to do is you need to set up the law of mass action, the equilibrium expression for this chemical equation. Then what you do is you calculate your concentrations. Remember, molarity is moles per liter. Calculate your concentrations for each substance. Then you're going to plug them into your equilibrium expression to calculate Q. Once you have Q, you're going to compare it to your K value. You're going to see, are they equal, less than, or greater than? Take a moment and first try to figure out what your law of mass action, your equilibrium expression would be. All right, so remember we're going to have products on the top, we're going to have reactants on the bottom, we're going to use square brackets, and we're going to raise things to the coefficients that are with each chemical. So this ends up being my expression. Now why don't you try to plug in your concentrations? All right. I end up with a Q value of 1.96. So now I have to compare K, what it should be, to Q, what's actually in my beaker. You should notice that K is larger than Q. If your Q value is too small, it meant your numerator was too small, your denominator was too big, you do not have enough product, you have too many reactants. So what's going to happen is your reaction is going to proceed to the right. The forward direction is going to initially happen. You are going to start making these Y and Z compounds until you get to the point where you're back at equilibrium. And at that point, the rate going forward and the rate going backwards will be equal. In the beginning, going forward is going to be more dominant, right? It's going to proceed that direction. Once your concentrations get adjusted, once you've made enough product, once you're back to equilibrium, forward and backwards rates are now the same. There is a way we can change our equilibrium constant. We can change the ratios that we need to be at equilibrium. There is one way and one way only to do this, okay? Here are some things that do not change your equilibrium constant. The concentrations? Nope. Changing the quantity of chemicals is not going to change the point at which that reaction likes to have equilibrium. Same with changing pressures. Does not change your K value. Adding extra solids and liquids. Nope. Does not change your K value. Adding a catalyst. Nope. You will get to equilibrium faster. The reaction will go faster until you get to equilibrium, but it will not change the ratios of your chemicals once you're at equilibrium. The thing that does change equilibrium constant is temperature. Every reaction will have a separate K value based on the temperature that it's at. If you're at 25 degrees, you have one K value. If you're at 26, you have a different K value. 27, a different K value. 28, a different K value. Every single temperature has a different K value. You have to know what temperature you're at to know which equilibrium constant to use. The problems that we do will assume that either temperature is being held constant or it would give you enough information to look up which one you would use. There are ways to determine what the K value would be if you had changed the temperature. Like you could do it mathematically, but that's the kind of thing we do in AP Chem, not here. Here you will be given enough information to just do a simple problem. What I would like to do on the next slide is go over a practice problem that's kind of like a chart. So what we're going to do here is we're going to see if changing one of these factors affects these various things. We have reaction rate, we have rate constant, equilibrium point, and the equilibrium constant. Be careful because the rate constant is a lowercase k and the equilibrium constant is an uppercase K. You got to be a little bit careful. We have a tendency to mix up the things that change the rate versus the things that change the equilibrium. So we got to kind of keep all this straight in our head. So if I change the concentration, yes, my rate of reaction increases. If I decrease it, it decreases. So changing the concentration affects the rate. Same with pressure, right? If we have gases instead. If I change the surface area, does it change the rate? Yeah, remember our sugar cube and our granulated sugar example? The more surface area you have, faster it can go. Changing the amount of solid and liquid. Remember, that's the one that's kind of tricky. It doesn't technically change the reaction rate. It may look like the rate has changed, but that's only because you might have accidentally increased the surface area that's available when you added more of your solid or liquid. But adding the solid and liquid in and of itself does not change the rate. Remember, solids and liquids don't have concentrations, so be very careful about those types of questions. Adding an inert gas. Nope, that's not going to change anything for us. It doesn't participate. Adding a catalyst, yeah, that for sure makes things different. That's going to speed things up for us. And changing the temperature, either heating it or cooling it, might make it go faster or slower. Now, changing the rate constant itself. Remember, there's not as many things that do that. Concentration change? Nope. Pressure change? Nope. Surface area? Amount? An inert gas? Nope, 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 nope. The only things that will give you a new K value for your rate constant are a catalyst, because it's actually changing the way the reaction takes place, and the temperature change. For equilibrium point, changing your concentrations does affect that. Remember, you got to find a new equilibrium. Changing the pressure, same thing, you got to find a new equilibrium point. But this time, changing surface area, solids and liquids, inert gases, catalysts, nope, 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 nope. Changing the temperature, yes. Remember, energy functions like either a reactant or a product, so it is something you have to take into account. Now, changing the equilibrium constant is not an easy thing to do. There's only one thing in this entire column that will result in a new equilibrium constant. All the way at the bottom. The only thing that will give you a new KEQ is a temperature change. I highly recommend that you go through and you spend some time, making sure you can understand which things get changed by which factors. The fact that there is some overlap here really gets people confused and you kind of start answering questions incorrectly. So spend a little bit of time, make sure you're really good and solid on this chart. Okay? All right, everybody, that is it for this video. I hope that was helpful. Bye.